So here's a tank question. Salt water pours into a full 20-liter tank at a rate of 20 liters per hour. The inflow initial concentration is 2 kilograms per liter, but after an hour the inflow concentration switches to 1 kilogram per liter. So that's the change, why this isn't just a standard tank question. We're going to need the Heaviside step for the inflow concentration. All right, but the first thing we have to think about before I even finish reading the question is, I'm looking through, does the inflow equal the outflow? In other words, I want to know if the volume changes or not. The brine in the tank is well mixed and drains out at a rate of 20 liters per hour. So the volume is constant. If the water flows, the brine flows in at 20 liters per hour and flows out at 20 liters per hour. So the volume is that constant 20 liters. The outflow concentration is always measured by Y. What is Y? Well, we're going to call Y of T. That's going to be the kilograms of salt in the tank. That's the unknown function. We don't know what that is yet. It changes. So the tank is initially full of fresh water, so read that as Y naught equals 0. That's our initial condition. So why is that? Oh, grams. It's kilograms in now. Got to change the problem. Kilograms of salt in the tank. Y prime is kilograms per hour. We're measuring our time in hours now. So how many initially, before we switch to the lower concentration of 1 kilogram per liter, initially how many kilograms per hour of salt are coming in? Well, it's 20 liters per hour and 2 kilograms per liter. So multiply those 20 times 2, and the liter and the on the top and the liter on the bottom cancel, and I get 40 kilograms per hour of salt are initially coming in. So let's write that out then. Let's put in this is our in concentration. The in concentration is initially 2 kilograms per liter, but then I want it to drop down to 1 kilogram. So I'm going to subtract Heaviside step function, which I'm going to turn on at an hour. I'm going to do all my times in an hour. And the function that it's turning on then is this, either put the -1 in the square bracket or minus. So let's check this in concentration. That'll be in the units of kilograms per liter. Before an hour, this U piece is 0, so it's 2 minus 0 times 1. After an hour, this U piece is 1, so it's 2 minus 1, or 1. So this in concentration then has the Heaviside step function, and it's doing what I want. Now our standard method for solving these tank questions is always inflow times in concentration. That's how I got that initial 40, 20 times the 2. And then minus out kilograms per hour, which would be concentration times flow. We're always multiplying the concentration times flow. I have here flow times concentration and concentration times flow, but just the product of the two minus the product of the two. When I think about setting this up then, Y prime is equal to the inflow, that's always 20 liters per minute. This in concentration, that's the thing that changes. That's the thing that has the Heaviside step function. But I'm putting it in the same spot as we would in our standard. Then I've got out concentration, Y kilograms divided by 20 liters. Since the inflow and the outflow are the same, the tank's always at 20 liters. And our outflow drains out at a rate of 20 liters. So now I've got my differential equation. Because it has a Heaviside step function on it, I'm going to solve it with Laplace. Let's multiply this out here. We got Y prime is equal to 40 minus, Heaviside step. I'm just multiplying that 20 through. And the 20s cancel top and bottom here, so minus Y. There's my differential equation. Now I'm going to take the transform, I'm going to take the Laplace of both sides. The transform of y prime is SF minus y naught. The initial concentration is 0. They told me that there was fresh water initially in the tank. Equals, okay, the transform of 40, a constant, is going to be 40 over S. The transform of the Heaviside step function is going to be e to the minus 1s. Now what's inside the square bracket? First we need to transform. Everywhere there's a t, I would put a t plus 1. There is no t, so I guess I'm done. Take the transform of 20. That's going to be 20 over s. And finally, the transform of f, of y is f. Okay, so now I'm good to solve for f. Let's bring the f over to the other side. So I'm going to have f times s plus 1 is equal to this piece. And divide everything by that s plus 1 bracket. Okay, now I've got partial fractions inside and outside, so I'm going to break this piece up into partial fractions. It wouldn't be too bad. I'm just going to ask the machine to do it. But you should be able to do it on your own. I should be able to do it on my own too. So that breaks this piece up, and then minus this. Okay, now I need to break that inside piece up into partial with partial fractions. But I mean, the only difference between what I just did and what I have here is the one I did has 40, the one I need to do has 20. So it'll be the same thing, but instead of 40, it'll be 20. So I can just take this and make that a 20 on top. Now I'm set to take the inverse Laplace or unLaplace. So the inverse Laplace of f is y equals 40 minus, 40 e to the minus t minus Heaviside step function turned on at 1. And now the square bracketed piece. The square bracketed piece on its own would untransform to be 20 minus 20 e to the minus t. 20 minus 20 e to the minus t. But the argument inside the square bracketed piece, the part that's switched on by the Heaviside step function, that argument has to match the argument of the Heaviside step function. So everywhere there would be a t, I put a t minus 1. And now, boom, I've solved the differential equation. Does it go through the initial condition of y naught equals 0? Yeah, because this u gets switched on at 1, so before 1 hour, it's 0, so this whole thing is not there before an hour. So 40 minus 40 e to the minus t, if I make t equal to 0, that's going to be 40 minus 40, or 0. Yeah, so it goes through the initial condition. If I wanted to write this as a split function, I could. There it is as a split function. Before the u gets turned on, after the u gets turned on to being 1. I just simplified because that'll be like 40 minus 20. Make that 20. Okay. That's the end of the question. That's the example. But what if I wanted to do this without Heaviside step function? What I could do, so I'm going to go back to the question here, and what I'm going to do is not worry about what happens in the second hour when the concentration changes. So I'm going to take this, I'm going to start again. The inflow in concentration, the out concentration and the outflow, the only thing that changes from what I've done here is in the first hour, it's 20 liters per hour times 2 kilograms per liter. So this is just plain standard. So let's go back up here. I'm ignoring the concentration switch. So what I'm writing down here is only good for the first hour. But it's fine. This gives me an equation that I could totally solve, because this is just y prime is equal to 40 minus y. That's first order linear of y prime plus py equals q. It's also separable. Let's just solve this. When I do end up solving this as a y prime plus py equals q, I kind of already know what I'm going to get. I get this. So this is the answer for the first hour. Now, what happens after that switch happens, and now the concentration is, the in concentration is now only 1. Okay, how much salt is in the tank at the time of the switch? In other words, what's y at 1 hour? Well, that's equal to, well, let's plug 1 in there. How many kilograms of salt are in the tank? Let's figure this out numerically. 25 and change. So after an hour, that's how much salt is in the tank. Now I'm going to restart the question. I'm going to go back. I'm going to restart time. So this is going to be my new why not. The new differential equation, inflow is 20, in concentration is 1, nothing else. So inflow is still 20, in concentration is now 1, outflow is 20, volume is 20, everything else is the same. And when I go to solve this equation, I have a new why not equals 25. But I'm restarting the clock. So when I mean time 0 now, it's my old time 1 hour. New time 0, old time 1 hour. So if I'm solving this, that's just going to be y prime is equal to 20 minus y. Solving this is going to be, let's write this as a differential equation then. My y prime is going to be y prime equals 20 minus y, and my initial condition is y naught equals 25 and change. So now I'm separating this out because this piece here is my new differential equation. I just need to solve this. So it's a y prime plus py equals q, but we can just ask the machine to solve it. All right, so here's what it gets. Y equals. This is the differential equation that's good for after an hour, but I have to restart time. So if someone were to ask me how much salt is in the tank at like 70 minutes, well, that's after an hour, so I would plug not 70 minutes, but 10 minutes or a sixth of an hour in here. If they said how much salt is in the tank at, let's say, half an hour, then I would go back to the original that I solved here and put in a half for time. If I wanted to make all of the equation one time, well, since this time is, like, I'd have to add an hour to my time here. So this would be t, like, plus an hour, to shift it an hour. If I wanted to put in 70, 1.5 hours, I'd actually put in a half here. So what I need to do is, I need to subtract 1 from my time. And now this is good for the times after an hour, and this is good for the times before an hour, but now they're the same time measured from the beginning because I'm shifting it in the second equation. So we have two options here. I think the Heaviside step 1 that we did originally is the easiest, but we can work around it by just restarting the clock and figuring out what the new initial condition is.